Hello everyone. Today we are going to talk about the analysis of heat exchangers, and before starting analysis of heat exchangers, I will introduce the logarithmic mean. What does it mean? And then we will talk about the logarithmic mean radius, because this logarithmic mean is very important in heat transfer and heat exchanger problems. So I have a cylindrical shell here, so it has some inner radius and outer radius, and here you have the wall with thickness of the T. Okay. And on one side of the wall you have T1, and on the other side of the wall you have the T2. And you can think the cross section as something like this one. Okay. Here you have some thickness. This is the cross section. And on one side you have T1, same cross section. Here you have T1, and here you have the T2, and then you have the inner radius and outer radius. Okay, so I will write the heat transfer in r direction. If I remember from my previous lectures, it is 2 pi k, the length of the cylindrical shell, and into T1 minus T2 divided by the ln of r out divided by r in. Okay, this was the result that we had from our previous lecture. Okay, so if you notice here, the temperature across the wall, so this one is T1 and this one is T2, the temperature changes in a logarithmic manner because you have the ln relationship here. Now comes the second part here. So what I will do now is that this one is a cylindrical shell cross section. I will write this one as a plane. Okay, I will think of this one as some plane. Okay, and this is the plane that I am thinking of. The same L, it has the same L, but this has been opened with a thickness of the T. Okay, it has the same thickness here. Okay, but this one is a plane. So I will now analyze the same stuff here. So here you will have the T1 and here you will have the T2. Okay, so if I write the heat transfer in x direction, it will be the area into conductivity, because it is plane, into the temperature difference divided by the thickness T. Okay, instead of T, I will write R out minus R in. Okay, so they are the same stuff, but here I am thinking of this one as a plane. So this is the geometry, and now it becomes a plane with some length. Okay, but here, if it is if it has a radius r, it will be 2 pi r here. But in our case, we have two radius. One is the r inner and one is the r outer. So if I open it as a plane, I will not have one r, but I will take the average r. So I will say that 2 pi r average. Okay, instead of this one. Because so same stuff happens here. This dimension here, it will not be 2 pi r1 r in or 2 pi r out, but it will be 2 pi r average. Okay, this dimension here, the same dimension that you have here. It's not r in, r out, but the average r. And here you have the L. So the area will be equal to 2 pi average r into the L. Okay, these two heat transfers should be equal because they are the same geometry. And then I will have the same conditions. 2 pi KL delta T, T1 minus T2 divided by ln R out divided by inner radius should be equal to the same stuff here. 2 pi the average R into L into delta T and into R out minus R in. Okay, so the 2 cancels out and the pi same here. The L, they are the same, delta T is the same. So I can write average R here. If I do that, average will be equal to the difference in radius divided by the ratio of the radius. Okay, you can see the case now. The same slab, so the same shell in plane geometry has a radius with a logarithmic relationship. The difference in them divided by the ln of these two ratios, and this one is called logarithmic mean. Okay, mean means average. So average, mean, they are the same stuff. Okay, and this logarithmic mean is used in heat transfer problems, because if you have a ln, if you have the ln function, in ln function to find the average, we don't do this one, r out plus r in by 2. Okay, this is not done in ln functions, but instead we are finding the difference and then the ln ratios of these values. Okay. Now, if keeping this one in mind, we will move on to heat exchanger analysis, and then you will use logarithmic mean temperature difference. Okay, now we will analyze a heat exchanger here. So this one is the tubular heat exchanger, or concentric tube, concentric tube heat exchanger. Okay, so we will analyze how temperature change inside this concentric tube heat exchanger. So I will show, let's say that this one is cold fluid, say that cold fluid moves in that direction and it leaves here, so they are not mixed, it flows over the tube, and we have the hot fluid, moves in that direction, okay, and leaves here. So this one is parallel flow heat exchanger. This one is T hot inlet, and this one is T hot outlet, and here you will have T cold inlet, here you have this part, T cold inlet, and here you will have the T cold outlet. Okay. Cold temperature outlet, and we will look for how the temperature changes across this along this heat exchanger. Firstly, I will draw the hot fluid, okay, how its temperature changes. So you will start with some hot inlet temperature, okay, and its temperature will drop, okay, but the temperature drop is exponential, okay, we should remember it. The temperature drops in a heat exchanger are most of the time exponential, and you will have a drop something like this one. I draw till the end. Okay, so this one will be drop in heat exchanger for the hot temperature, and this part will be the hot outlet. Hot water temperature inlet, this one is some inlet temperature, and it drops to outlet temperature over here. Okay, this one is the hot outlet. Now I will look for the cold water. So here you have the T cold outlet. Okay, it is here. You have the same stuff, and you will start with some low value of the water temperature for the cold water, T cold inlet. This one is low, and its temperature will start to increase. And these two, you will have always a temperature difference between them. So let's use another color here. So between these two, you will have delta T x. Okay, why x? Because it changes with x. So you can see here you have high temperature difference, low temperature, and drops, and as the temperature delta T x drops, so it means that Q dot drops. So heat exchange between these two fluids, one fluid gives of its heat to the other one. Okay, but if the heat exchanger is too long, if heat exchanger is too long, you will have T cold outlet. This one is a cold outlet. Let me write it here. So T cold outlet will be almost the same as T hot outlet. So it will be almost the same as T hot outlet. Okay. But in this case, they are not equal. Okay, this one is the temperature change across the heat exchanger, along the heat exchanger, and we'll look for in the similar manner. We'll look for logarithmic mean temperature difference, and also how the heat transfer in this heat exchanger. So firstly, hot fluid Q dot hot fluid will be equal to its enthalpy change, and the enthalpy change can be written as the flow rate of the hot fluid into its Cp value, okay, and into hot fluid inlet temperature minus hot fluid outlet temperature. This is the first equation, and then you will have the second equation, Q dot for the cold fluid, the same equation, M dot cold fluid, and the Cp of the cold fluid, okay, because cold fluid has some M dot and it has some Cp value, and then T cold, you can use outlet temperature or inlet temperature. If you are looking for the positive values, then you will look for this relation, outlet minus inlet temperature. This one will be the second equation. And you can have the third equation, and the third equation will be that instead of these two values, I can write, so in ideal conditions, this one should be equal. Okay, in real conditions it is not, but in ideal conditions these two values are equal, and they are also equal to, these two equations are also equal, and they are also equal to a second, if one more equation, which is u, u overall heat transfer coefficient, we have talked about this one, u surface area into LMTD. Okay, and now this LMTD is the logarithmic mean that we have talked about, so it will be LMTD. This one is logarithmic mean temperature difference. Okay, logarithmic, this one is the mean, you can see the logarithmic mean, but instead of radius you will have the temperature difference. Temperature difference. Okay, and this logarithmic mean temperature difference is this T hot inlet minus T cold inlet. So right here it will be T hot inlet minus T cold inlet. Okay, minus, so first these two temperature difference here, and then these two temperature here difference. It will be T hot outlet minus T cold outlet. Okay, T hot outlet minus T cold outlet divided by their ln. You can see the value difference of the values divided by their ln ratios. T hot inlet minus T cold inlet divided by T hot outlet minus T cold outlet. Okay, this is the logarithmic mean temperature difference for this parallel flow heat exchange. Okay, so this is the three equations that we have. Okay, and you will have also the F value here, and you will have one more value here, which is the F, UAS into LMTD into F, and the F is correction factor. Okay, and for this heat exchanger it is 1, therefore no need to calculate the F value here. So you have three equations, and we will have one more equation we will talk about in our next slides, but for the case now these three equations are enough. And as you notice here, since the temperature changes are in exponential manner, the temperature difference should be in logarithmic manner too. Okay? This is the first case of the flow in heat exchanger. Now comes the second case. In this second case, instead of having the parallel flow, this one was the parallel flow, we look for the counter flow. So in that case you will have, this one is, let's say, cold fluid, it moves in that direction and leaves up here. So T cold inlet, and here we have T cold outlet. For the hot fluid I will use the opposite direction, so you will have the inlet here, T hot inlet, and then it moves in that direction, and the T hot outlet. Here we are having the counter flow. For counter flow heat exchanger, the temperature will be something like this one. So, and by the way, here you have the L, the length of the heat exchanger. So it has some length, and this length is the L. L is length of the exchanger. So here you will have the same L here, but firstly I will start from the hot fluid inlet temperature. So let's say that I am somewhere around here. I start with hot inlet temperature, okay, T hot inlet, and then the temperature will drop in an exponential manner, as we have said in our first slide. Drops some value here, T hot outlet. You can see the temperature of the hot fluid drops and to some outlet value. And now I will draw the cold fluid temperature, and cold fluid inlet temperature starts somewhere around here. This one is, let's say, T cold inlet temperature. I don't know the temperature value, but I assume somewhere here. And it increases in an exponential manner. Okay. And this one is T cold outlet. Temperature first with low value and then increases with some outlet value. Okay, so you can notice the main difference here. Here the cold outlet temperature of the water cannot reach hot outlet temperature, but at the maximum case it can reach. But here you can see cold outlet temperature of the heat exchanger is more than hot outlet of the heat exchanger. So if I draw it, you can see this one is more than that one, so it has more effectiveness. You can notice the difference here. So you will have the same equations here. So equation number 1 will be Q dot hot, and you will have M dot Cp hot, this one is hot, T hot inlet minus T hot outlet. And the second equation Q dot cold will be M dot cold, Cp cold, T cold inlet minus T cold outlet. The third equation will be Q dot C is same as Q dot H in ideal conditions, and you will have again U AS LMTD into F, and here F is again 1, and LMTD will be the same LMTD equation, the temperature difference at inlet. You will have T hot at inlet, T hot inlet minus T cold inlet minus T hot outlet minus T cold outlet divided by their Ln ratios, T hot inlet, T cold inlet, T hot outlet and T cold outlet. Okay. And this one will be the 3 equations, and you will see that we will have one more equation in our next slides, but for the case now it is enough. And I will add one more thing here, is that M dot into C, it is called heat capacity, and it is shown as C. So if it is M dot Cp of the hot one, this one is Cp, and you will have C hot, and M dot Cp cold, you will have the C cold. Okay, this is the nomenclature that we are using. Okay, now we will look for what happens when you have the phase change. Okay, but first we will look for the boiling, okay, and then we will look for the condensation. Okay, say that you have a fluid here, okay, that moves in that direction, this one moves in that direction, and here you have another fluid. Okay, and let's assume that one fluid is very hot, this one is very hot, and this one is, let's say, boils. It has low temperature and it boils. If you remember from thermodynamics, so I will write the equation here, Cp delta T, and if you remember from thermodynamics, when you have the phase change, this term is 0 in phase change. Okay, when the delta T is 0, Q dot is not equal to 0 because you are giving it a heat to have the phase change. This one is not 0, and then you will have Q dot by 0 will be Cp. Okay, that means that the Cp value tends to infinity. Okay, Cp is very large. So in phase change processes, Cp value is very large. Firstly, I will look for this part, which is boiling part. In boiling part, for the cold water, the temperature doesn't change, and you will have something like this one. It may be another color here. This one is the fluid that boils. Okay, it will. This one is the fluid that boils. It starts with a constant temperature. You will have, this one is the L, the length of the heat exchanger. But for the hot fluid, its temperature will drop. And it will start with some value here, and it comes, drops, value here. So this one will be hot inlet, and this one is hot outlet. And for this boiling process, you will not use M.Cp, but you will use, for this one, for Q dot, you will use M.HFG. Okay, so this HFG is from tables. Okay, we will look for the temperature. This is enthalpy of vaporization, and you will write this value, and into M dot you will get Q dot for this one. Again, you will have heat transfer in that direction. Okay, now comes the LMTD relation doesn't change. You will have the same difference across it. Now comes the opposite case. We will have the condensation here. So for the condensation process, so what will happen is that this one will be hot and the other fluid will be cold. This one is cold and this one is cold. And for the hot fluid, again, let's choose some direction here. This one is the flow direction, and for the cold fluid, you have the same flow direction here. So it is parallel flow again, you have some length here of the heat exchanger. And for the hot one, the temperature doesn't change. This one is T hot, but for the cold one, which increases its temperature, it will be something like this one. Okay, T cold. So this one is T cold inlet, and this one is T cold outlet. And this again you will use for the hot one, the enthalpy of vaporization m dot HFG, and for this one you will use m dot Cp and delta T of the cold. And also the LMTD relation is there. You will look for the difference here, and you will look for the difference here. Okay, again here you will look for the difference here, and you will look for the difference here for LMTD. Okay. And then now comes to analyze heat exchanger problems. The first is LMTD method. So we are looking for size problems in LMTD method. Size is very important. And we have three equations. We have talked about this one, UAF LMTD, and we have said that F is 1 for counterflow and the co-flow. Co and the counterflow, it is 1. And for other heat exchangers, look for the F value. And here we have a chart for the one heat exchanger, which is single pass cross flow heat exchanger. And for different ones you should look for the chart, and first you should find the R value. R is T1 minus T2, this one is T1 and this one is T2, and T2 minus T1. Okay, this is the R value, and then you look for the P value, which is T2 minus T1 and T1 minus T1. Okay, and let's say that R is 3, okay, and the P value is, this one is the R value. Let's say that R is 3, this is the axis for R, and you look for the P value and say that P is 0.2, and you go from 0.2 to 3 value curve, and then you find the F, which is 0.95, or it can be 1.5. again the intersection, let's say this one is 0.6, and then this value you will get the correction factor, which is 0.55. Okay. This is the first method, and the second method is epsilon NTU method here. And the first, what is epsilon? Epsilon is the effectiveness. This one is effectiveness or efficiency, you can say, and compares the heat transfer of real value with the maximum heat transfer value. Q dot maximum. This one is the effectiveness, and then you have the NTU, and the NTU is number of transfer units. Okay, a number of transfer units, and it is UA divided by m dot Cp. And for heat exchangers, we take the minimum value of m dot Cp, but generally it is UA by m dot Cp. And what does it show us? It is the size. NTU means size of heat exchanger. Okay. Because if NTU is large, it means that the size area, which is the value that you play with, area is large. So if you make NTU large, area large. Area large means the length large, because area is perimeter into the L, and then you will have cost and plus weight. Okay. Therefore, most of the time NTU is less than 3. Okay. It is the rule that we use. And then you have the epsilon. I've talked about this one, maximum heat transfer, and the maximum heat transfer happens, okay, it happens when you have the maximum temperature change, delta T maximum. Okay, and this maximum temperature change happens, if you look at the charts, you have the maximum temperature change between this one and that one, hot inlet and the cold inlet, or again hot inlet, cold inlet. This is the maximum heat transfer happens. So therefore you have hot inlet minus cold inlet. This is the maximum heat transfer. It is proportional to, and this maximum heat transfer happens with this maximum temperature change, and the delta T maximum can happen when m dot Cp is small. Okay. Because if the Cp value is very large, its temperature will not increase, because it is very large Cp value, that delta T becomes small. If you look at here, Cp is very large, delta T will be small. So if delta T is very large, then this means that this combination is very small. Okay. So this should be logical. If you take the large value, maximum value of delta T, and you should look for the minimum value of this one. So you will look for the minimum of this one, and maximum of that one will give you the maximum heat transfer process. And then minimum is minimum of CH and the CC. We have said that C is m.cp. We have talked about this one. And then epsilon, to find epsilon, it is function of NTU. You should look for the chart or the formula. And in the charts and the formula, you will need the C value. It is C minimum by the C maximum. And then you will find either Q dot if it is unknown or outlet temperatures, because in this relation LMTD, this logarithmic relation, to find temperature is very difficult. Therefore we use epsilon NTU method. Okay, so here we have a chart for epsilon and the NTU, and as you notice here, this is the first thing, that this chart is plotted for when C is 1, because you can have different values for the C. And when C is 1, you can see that for other C's also, for other C's, till the point of 0.3, okay, all heat exchangers show the same performance. Okay, it doesn't matter if I select this heat exchanger, that one, it doesn't matter, they have the same performance. Okay. And after the value of the 3 or 3.5, something like this one, you can see effectiveness don't change too much. Okay, after the value of 3, or you can look for 3.5, it's also okay. Effectiveness don't change too much. Okay. This is the process where we are looking for. And as you notice here, the maximum effectiveness is for counterflow heat exchanger. It has the maximum effectiveness. And then you have the second one, which is the this one is the cross flow. Till some point it is cross flow, till after some point it is cross flow, and till that point you have shell and the tube. And here you have two shells and n number of tubes. This is shell and the tube. You have the two shells, and then comes again cross flow with one fluid unmixed, and then shell and the tube again, and the minimum is this one, minimum, and this one is the maximum. The trend is similar for other values of the C. And comes the last part of the analysis of the heat exchangers. When the C value is very small, when C is very small, it means that C hot or C cold tends to infinity. Okay, we have said that if you have boiling or if you have condensation, or it is also possible that you have a pipe and you have environment, okay, and the environment has a very large C value. It has very large C value, and the pipe C is very small with respect to that one, therefore the ratio becomes very small. In that case, all of the heat exchangers has the same efficiency. Okay, and the effectiveness becomes one relationship, which is 1 minus exponential of negative NTU for all heat exchangers. For all heat exchangers. This is the special case for the heat exchangers. Okay. And now comes the problems in heat exchangers, and we will solve it in our next video. Best wishes.